Now, so therefore, for example, the antinodal lines will be, here is one antinodal lines, 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 here is one antinodal lines. So these places where you have the maxima essentially also tells you about the separation between antinodal lines. Okay. Now, this is case 1. Now, case 2 will be talking about path difference, which is more common when you talk about water waves or sound waves. The whole situation is described in terms of path difference. So there are some rules. For example, in DSE, you need to know that the path difference, when it is equals to 0, lambda, 2 lambda, etc., then I will have constructive interference. If you are given the path difference, if you find out that the path difference is equals to half a lambda, 3 half a lambda, then you will have destructive interference. In terms of lines, it means that you will be on antinodal lines. Or in terms of destructive, it will be you are on nodal lines. Antinodal lines and nodal lines. Now, so, well, what are the possibilities they can ask? Well, one possibility is they give you two sources. So let's say this is S1, this is S2, and they ask, I tell you that this is a length, a point P here, and I say that this, let's say, point Q here, and then I tell you that S1P equals to 12 centimeter, S2P is equal to, let's say, 10 centimeter. And then S1Q is equals to, let's say, 30 centimeter, and then S2Q is SP first. Okay, S1 like this, and then I tell you that the wavelength is equals to 2 cm. Then in this case, what do you mean by finding path difference? Will be you find the difference of S1P and S2P. So the path difference at P will be S1P minus S2P, which is 2 cm. And 2 cm is one wavelength, because it's given that the wavelength is 2 cm. So therefore, from the above, we will conclude that you will have constructive interference at P. And then other thing they may tell you that also S1, S2 is equals to XCM. And then S1Q is equals to 21 cm. Then in this case, we can again find the path difference. Oh, I can find the path difference. How? For the path difference at Q, what would that be? in this case. Look carefully. Michael, what's the path difference at Q in this case? This is testing you whether you are following the flow. Just I give you two numbers and you subtract. If you try to subtract 21 by 8, then you fall into my trap. Now, path different means, I go back to P. P is very standard because it is at that location. And many examples are using this. Path difference means you find the difference between this and that, and you subtract them. Okay, using that coloring here. Now, however, for Q, what you should do is you should subtract this with this. No, with this.
Yes. So it's 8.
It's actually just 8 cm. So in this case, the path difference is just equal to S1, S2. This is just the separation between the two sources, which is D in the above formula, the slit separation. So therefore, in this case here, you take the plate. No, you take the slit separation as the path difference. So this is equal to 8 cm, and this is 4 lambda here. Therefore, you have constructive interference. So therefore, at this point Q, you have destructive interference. Constructive interference. This is one way they can test you interference using path difference. Well, there is another way they can test you about interference using path difference, which is they give you wave fronts. So it's very difficult to draw. Let's see, I'm able to do it. What they do is that they give you two sources. And then the two sources producing the interference pattern accordingly. Yeah, like this. And then what they do is that you have this kind of spherical wave fronts in the figures. And now what they do is that they produce two such a wave and they put them together. Diagram like this. So now every time when you're given this kind of so many circles, you need to read the notation first. There are two types of notation. One situation is these lines, they are all crest. In a diagram. So in this case, then this will be one wavelength. Similarly for the blue one. Now, however, some questions, they do not just show you the crest, but they also show you the trough. What they do is that they will put some dotted line between two crests. That will also happen, which we do not know, well, which can also be in the exam. They give you dots to show you the truth. They need to pay attention to.
God, this one is so...
Now, then, let's see, then how to do it. Well, usually what they do is that they give you a point. Let's say a point here. Let's say call it point P. Then you need to deduce whether you have constructive or destructive interference at point P. Well, the way I do it is, you just can't. Maybe I denote this as S1, this is S2. Then from S1 to P, I have traveled 1 wavelength, 2 wavelengths, and 3 wavelengths. So therefore, in this case, I do not need to find the path difference in meter and then convert into how many wavelengths. Because this diagram is already in the unit of wavelength. So 1, 2, 3. So in this case, is you can't. S1P equals to 3 wavelengths. And then you can't. S2P equals to 1 wavelength, 2 wavelength, and a half. So therefore, the S2P is equals to 2.5 wavelength. Is you can't, not given. So therefore, in this case, I can find the path difference. And then the path difference here will be 3 wavelength minus 2.5 wavelength. So you got 0.5 wavelength. So you can conclude that you have destructive interference at P. So this is an example of how to use the path difference to solve interference questions. One just very obvious. You are given these wavefronts, then you can't.
Just count.
Yeah, this time not given any wavefronts, then you need some trigonometry to find out the length. This one is you have all the lengths. You even have the slit screen separation. You even have, let's say, the slit separation. Then you can use this formula. All these 3 types of question, they are all about double slits because they are about 2 sources in the questions. Now, then, closely related to double slit will be the diffraction grating. Then, for diffraction grating, you need to know about the formula. So the situation is you have a diffraction grating, you have a beam of light shining on it with a wavelength lambda, and then it will be able to arrive on the screen and it forms different orders. So in this case, we do not have those interference pattern we see before. Instead, we will just see the maximum. So you have a peak here, peak here, peak here, peak here, and a peak here. So this is similar to the one we have for here. But for double slit, you can see like curving down slowly and then touch 0 and then come back. This is double slit. You will see so-called a fringe. Fringe means you have a finite width of the fringe. So you can talk about delta Y. But for diffraction grating, you don't see a fringe anymore. You just see a very bright dot there. So because of that, we call that order. This will be m equals to 0, the 0th order maximum. And then on the other side will be the first order, second order, etc., etc. So you have the m be the order in the question. And then on the diffraction grating, you are usually given the characteristic of this diffraction grating. One way to do it is they may tell you directly the slit separation. This will be the slit spacing. They use the term spacing. Another possibility is they do not tell you the slit spacing, but they tell you that you are given, let's say, 300 lines per mm in the questions. Then we need to find a d ourselves. 300 lines per mm, it means that in 1 mm, that means 1 times 10 to the power minus 3 meter. You divide this length into 300 identical pieces, so divided by 300. So either this on the left or the one on the right, which tells you the slit spacing of the diffraction grating. And then finally is the corresponding angle. So this one will be the theta for m equals to 1. And then this one will be the theta for m equals to 2, etc., etc. Yeah. I don't know how I call it. I usually just call it like angular position. This theta will depend on which order you are referring to. You used to say m equals to 0, that is very simple. Theta is just equals to 0 for the 0th order maximum. But for theta equals to m equals to 1, 2, 3, then they are all different. Okay, with all this defined, then we have d sine theta equals to m lambda. This is the equation for diffraction grating. So in examination, I expect you to recall this formula whenever you are doing calculation for diffraction grating. This is the first step. If you can't recall this equation, then never mind, you skip this question. If you can recall this equation, the next step is, do you know m is order? Do you know d is the slit separation? Do you know how to find d when you are told that you have 300 lines per mm? Things like that. Okay, now then for these questions, then what kind of thing we can discuss? First of all, is about the dependency on the wavelength. According to this formula, d sine theta equals to m lambda, then I found that sine theta in fact is equal to m lambda over d. It means that if you have a longer wavelength, then we would expect to have a larger angle theta. Now, this goes back to the idea again, if you use red light at first, and then you turn it, I don't use red light, I use violet light or blue light. Yeah, sorry, it's the other way around. So if you are using violet light at first, and then you use the red light instead, then that means you increase the wavelength. Then you should see that the maxima, they will now spread out with a larger angle theta. So therefore, that's why on the screen, usually what you find is you will find the red at the center may be the two colors at the same. But in the first order maximum, then you will have the red with a smaller angle, while the violet will have it's the other way around, sorry. The purple should be closer to the center, while the red will be further away from the center. So you will see this is the first order maximum. This is the first order maximum. This is the 0. And then again, for m equals to 2, you expect to see the red should be further away from the center. The red should be further away from the center. For m equals to 2. This is a dependency on the wavelength. This should be like all color in the middle. Now, this is dependency on wavelength. Another one we usually ask will be about the question on maximum order on the screen, or they will phrase it as the number of bright or the number of maxima on the screen. Well, here, the maximum order will be the maximum value of m, while number of maxima on the screen will be 2m plus 1. Because you always have 0 order at the center, and then m equals to 1 on both sides, m equal to 2 on both sides, so 2m plus 1. This is also a very common type of question. What they use is they recall one very important mathematical fact. Sine theta is smaller than or equals to 1. When you have this, then you will have sine theta smaller than or equal to 1. That means m lambda over d is smaller than or equals to 1. Because we just learned that d sine theta equals to m lambda. So mathematics tells you sine is smaller than or equals to 1, while physics tells you that sine theta equals to m lambda over d. So therefore, lambda must be smaller than or equals to lambda over d. So therefore, for some calculation, let's say I give you lambda over d is equals to 2.3, let's say. Then the maximum order m you can have will be 2. That means I should have 2 times 2 plus 1, 5 maxima on the screen. So there's one remark is to remind that this result is independent of the distance of the screen. Let me write this down. It's independent of how far the screen is. Because someone will say, now maybe you got only 5. Maybe can I like move this screen further? May I move this screen further away? Then I may able to capture more and more order. The answer is no. Because mathematically, what determines the maximum order you have in an experiment, it only depends on the wavelength and the slit separation, but not the screen slit separation. So no matter how close or how far the screen is, the number of order you can find for a diffraction grating remains unchanged. Well, lastly is to find the width of the spectrums. But what does that mean? It means that when you have diffraction grating, and then you will have, this is the 0th order, and then you will have, let's say, the first order spectrum here. And then what we want to find here is to find the width of the slit, to find the width of the spectrums. So that means I want to find here. I want to find x. x will be the width of the spectrums. And we need to find out. But this is not easy. Now, let's suppose that we are given we are given the wavelength for the red, the wavelength of the violet. You are given the D, that means how far the the diffraction grating and the screen. You're given the slit separation D. You're given all this. And then you need to write X in terms of lambda, D, and D. Now, how to do? This one, you need to recall the fact that actually a spectrum is made of many colors. On one side, you should have red here. On the other side, you will have violet. And then you will also have other color in between. For example, you may have green, yellow. I just draw it out one like this. Now, the red light will be on the further away from the center, while the purple light is near the center. While in the middle, then you will have those yellow, green, other color. So now, how can we find this width? Well, the starting point is you still use the equation for diffraction grating first. Now, I can find the angle for different colors of light. For red light, I can find the angle which is arc sine m lambda over d. I'm talking about the first order, so I just make m equals to 1 later. And I can also find the theta for the violet light. With red as a wavelength, with violet as a wavelength here. So therefore, you can find these two angles with a direct application of the diffraction grating formula. Well, but that is not what we need. I want to find this x here. Well, then we need trigonometry. So on the screen, what happened right now is you have this as the D, and then you have two lines. Or what you find is you find this as theta red, and this is the theta violet. In the center, you will have violet light here and a red light here. Well, how do I find x? I can find out this length here, in fact, is equals to d tangent theta red. And then this length here is d tangent theta violet. I'm using a trigonometry here to solve the things. Now this one, you may not able to find it in your past paper, but it's in your textbook. So, amazing. Which part? Yeah, but this is in your textbook. No, not our syllabus. No. It may. I don't. Yeah, it may show up in your exam. Yeah. Because this is not a question they put it in like a shooting the stars or challenge question. No, this is just a worked example. And the worked example in your textbook, they are actually quite they match or they are quite consistent to a DSE style question. Yeah. But of course, if they test you this, it must be a long question. It won't be a multiple choice. So, no, because it's difficult, or because it's too long. Therefore, this question is nice in the sense that it tests you the use of this formula. This is just direct application twice. And then here, they test you whether you can see the difference between these two variables. But anyhow, I think as I prepare or as I study the diffraction grating or double slit, I always need to remind myself that occasionally I will need to use some trigonometry, sine, cosine, tangent to solve the problems. It is just similar like when you draw free body diagram, I need to resolve forces into vertical and horizontal component. I expect to use some trigonometry. But this is also the place you can use the trigonometry. So therefore, the length x, then we just use these two to find out. If you want to have practice, you can go to the worked example in your textbook. I think it's in the topic 13 or 16. Oh, then you can find that one and write that out once if you want to practice. Oh, yeah, this is the diffraction grating and the double slit. It's about 1 hour. I think you need a break, and also you can't focus that long. For the rest of the hour, you can just ask me questions. You need some time to do.